Good morning, everybody. We're going to talk a little bit about the future. So climate science is quite a young science, and the question which it's been trying to answer has evolved a little bit over its 30, 40-year existence. And at the time of the first assessment in the early 90s, the question was primarily about the fundamental mechanisms of how the Earth system would respond to greenhouse gases. It was a question of can it happen and how would it happen? And then by the time we reached the early 2000s, the focus then became on detection of the climate signal. Is it happening? What's causing it? And then as time continued, the signal got increasingly clear, and that question became increasingly well answered. And by the 2010s, the focus switched to how bad could it potentially be? What is the idealized sensitivity of the climate system to increasing greenhouse gases in the future? But now, it's almost been weirdly shocking for the community that only now we're really focusing really hard on the question of what we can do in terms of what are the actual mechanisms for changing our industrial and economic and physical systems to actually do something about climate. To get the basic science over with quickly, it's now the signal that we have, the observed temperature signal, is impossible to explain without the effect of humans. The way that we'd classically do this is we'd run climate models in an idealized way using greenhouse gases and aerosols and everything, and then we get one simulation. But then we can run them again without the effect of greenhouse gases, with only natural effects, and we get the green curves here. And then we can run it with only aerosols, and we get the blue curve down here. So what we see is the warming which we see at the moment is some combination of the effect of greenhouse gases, making the system significantly warmer, and aerosols making it cooler, though we're more uncertain about the effects of the aerosols. But one, perhaps the most important result which has come out of climate science in the last 20 years is this one, which says that basically the climate system follows quite a simple rule. So for every ton of carbon we put into the atmosphere, the Earth warms by the same amount for an extended period of time. So it doesn't matter when you emit that ton. You could emit it today, you could emit it in a year's time, you could emit it in 10 years' time. You still get the same amount of warming once you've finished. And so this proportionality gives us a lot of power to a lot of control over the degree of warming which we have in the climate system. And it's worth noting that it's not only carbon we're dealing with, it's carbon which follows those rules. But there's other things which affect the climate system as well. But really, it's useful to break it down into three. Carbon follows the rules which we're talking about before. The more we emit, the more we warm. And the contribution of carbon to our warming has increased and is increasing significantly over the last 20 years. Methane is a very powerful greenhouse gas which responds differently. So methane, as soon as you stop emitting, the effect of the methane begins to decline away over a time period of 20 years or so. And so that effect will decline over time. And then we have everything else, which is red, which is a mix of aerosols and other greenhouse gases and other stuff. And so that's controlled a lot by pollution measures. So let's do a very simple experiment. What would happen if we just stopped emitting everything today? Well, it would look something like this. So the blue curve is carbon. Again, this is the present day. Boom, we stop. The carbon remains, the warming associated with carbon remains roughly constant throughout the end of the century. The methane proportion declines away, and then some complicated stuff happens with the rest. Where do we need to get to? So the Paris Agreement in 2016 made statements about the need internationally to keep temperatures below 2 degrees. And there's good reasons for this, because lots of bad things happen even at temperatures potentially below 2 degrees. And so one field which has moved in a lot over the last assessment of the IPCC is that we understand quite a lot more about regional changes which are potentially irreversible at warming levels which are around 2 degrees or even sometimes less than 2 degrees. And so there's really very good reasons why, as a species, it's a good idea to keep temperatures below 2 degrees. And that's why we're having this conversation today. So what do we need to do? So let's return to this nice result that we have, that the more we emit over time, the more warming we get. So this is the amount of emissions which we've had since the beginning of the industrial revolution. Increasing. This is 1 trillion tons of carbon. This is 2 trillion of carbon. No, this is 1 trillion tons of CO2, 2 trillion tons of CO2, 3 trillion tons of CO2. And we are here today. And so what we can do is we can say, okay, we have a budget. We don't want to exceed 1.5 degrees. And then we can use this relationship to tell us, translate that into carbon. That gives us a budget of carbon to remain below 1.5 degrees. And so this is roughly the amount of carbon which we have left to keep temperatures below 1.5 degrees. And this is what global emissions have done over the last 30 years. They rose steeply in the 2000s, and over the last 5 years or so, they've sort of stabilized, but not quite. There was a small dip during COVID, but then it kind of bounced back up. So this is where we stand. Okay, so this is emissions every year as a function of time. So what does our carbon budget look like in this space if we just carried on emitting at the same rate as we're currently emitting? This is today. This is 400 gigatons of carbon. This is how much we have to stay below the 1.5 degree target. That takes us to about 2033. At that point, according to our simple cumulative emissions relationship, that's when we would have a 2/3 chance of exceeding 1.5. If we decided that we don't care about 1.5, we care about 2, we gain ourselves another 20 or 30 years. So let's assume that we still have interest in thinking about 1.5. This isn't a very realistic scenario. We wouldn't just go till 2033 and then stop. So let's do the next the next thing, and we'll just assume that we linearly decline starting from today to net zero. So if we do that, that means that gives us a net zero date of about 2042, 2043. But the rate of decline associated with this is enormous. So note here, this is COVID. Remember what COVID was like? Remember what the perceived reduction in emissions during COVID was like? You need to do that every single year. And that's what's implied for meeting the 1.5 degree target. So obviously, when we run climate models, we don't just draw a straight line from present day emissions to net zero. We create a scenario. And so scenarios take climate targets. So climate targets, for example, like keeping warming below a certain level. And then they translate that into pathways for different sectors, into the pathways for the energy sector, for transport, for industry, for food. And we can make different decisions about how those targets are implemented. So there's once we expand these degrees of freedom that we're dealing with, there are different moving parts. We can do some things faster than others, or we have some control over the amount of potentially negative emissions in the future. So let's talk about that a little bit more. Okay, so we have our carbon budget from before. Let's go back to the straight line scenario. Very difficult to achieve. And so what a lot of these models then do is that they borrow from the future, and they do this. So they choose a line which is less aggressive, getting you to net zero in 2060 or so, but then after that, assume a period of net negative emissions. And so different scenarios assume that these net negative emissions are carried out to different extents. So for some scenarios, we assume that there's very little capacity for negative emissions in the future. For other scenarios, we assume that we'll be able to pull out similar amounts of carbon to the amounts that we're emitting today. And so Rosie's going to talk about that a little bit more in a minute. So I'm not going to dwell on that too much, given my time is nearly out. But what I will talk about just a little bit is geoengineering, which is a topic which is increasingly talked about as not as a solution, but as a last measure for preventing warming from exceeding a certain level. And what geoengineering, there are different approaches to geoengineering, but most of them involve making some sort of temporary change to the radiative balance of the planet, either by emitting sulfates into the stratosphere, or making clouds brighter, or removing cirrus clouds, and so the Earth can radiate more easily. But in each case, it requires you to do something continuously. It requires you to send aircraft into the sky continuously to make a change to the radiative balance of the planet. And the idea is that you do something like this. The idea is that you overshoot the target you want to reach and then come back down again. But in the meantime, you have a huge campaign to change the radiative balance of the planet. And then once your concentrations are coming back down again, then you can ramp down your emissions. The problem with this is that there's a lot of things you don't know when you start doing this. You don't know how sensitive, you don't know how the Earth is going to respond on that downward branch of the heavy negative emissions phase. You don't know whether you can pull off the negative emissions, and you don't know how well a geoengineering is going to work. And so when you take all of these factors into account, you can start off expecting to do geoengineering for 50 years, but you might actually be doing it for 500 years or more. And so, are we doomed? I'm going to leave Jan to answer that.
Okay. Thank you. And, I'm going to talk about a concept that is getting more and more relevant, and it's called overshoot. And it's about exceeding a warming level and then returning to that warming level again. But if we start by looking at the recent temperature development since 1850, we see that the current warming, the last 10 years, is approximately 1.1 degree Celsius. So we see a quite clear warming. And in the recent synthesis report, we used the opportunity to update that number to 1.15. So we see a clear warming trend, as you know so well, after you have read all the IPCC reports, I guess. And so that is the past and the warming up to the current. And for the future, Working Group 1 used 5 main scenarios. And here you see the time scale up to 2100, and here you see the CO2 emissions. And you see 5 scenarios. There's one very pessimistic with very high emissions, and then one with high emissions, and the intermediate, and then low and very low. And these 2 blue scenarios, they are very optimistic. They cross the zero line in the 50s and in the 70s. So this is the famous net zero concept. And below that, we talk about negative emissions. And I put a question mark here, because we don't know how to do this on a global scale. And Rosie will talk more about that. So with these 5 main scenarios, Working Group 1 calculated or assessed the temperature development over this century, the global mean surface temperature in response to CO2 emissions, and also other emissions like methane and nitrous oxide. And the first thing we see is that all the scenarios, from the very optimistic to the pessimistic, they cross 1.5 in the near term. And we also see that this blue scenario here stays just below 2 degrees. So these 2 lower scenarios, the blue scenarios, they are compatible with the ambitions in the Paris Agreement, which says stay below 2 degrees and pursue efforts towards 1.5. But as I showed you, these are very optimistic. And based on this, I think we should be prepared to handle a situation where we cross 1.5. But we need to be aware of the difference between crossing a warming level and a single-year warming. So we may, in a single year or a couple of years, be above 1.5. That does not mean that we have crossed that level. We have to be patient, and we have to average the temperature development over 20 years. That's what we did in IPCC. Because there are huge natural fluctuations, so a single year or a couple of years does not mean that we cross 1.5. So if we cross 1.5, don't think that it's that we are doomed, as Ben talked about. Be patient and listen to the science when we do the averaging and consider what is happening with the temperature observations. So working group 1, the physical science basis, we considered 5 main scenarios. But working group 3, they had hundreds of scenarios. Actually, 1,202 scenarios to be precise. And here you see the cloud of scenarios in the total IPCC report over the century. And here is the warming relative to what we call pre-industrial, a proxy for the pre-industrial conditions, 1850 to 1900. And only very few, 6 or 7 scenarios in this cloud of scenarios stay below 1.5 all the time. So based on the current knowledge and the current scenarios available in the literature, we again need to be prepared for crossing 1.5. But that does not mean we are doomed, and we may bend the curve again. So working group 3 says unless there are immediate and deep emissions reductions across all sectors, 1.5 is beyond reach. And this is quite strong and serious message from working group 3. Immediate and deep, all sectors. And limiting warming to 1.5 with more than 50% chance, or 2 degrees with more than 67, involves reaching global net zero CO2 emissions in the 50s or 70s, along with deep reductions of other greenhouse gases, especially methane and nitrous oxide. So this is a very strong message from working group 3 again. And here is another, I would say, strong graph from the synthesis report, which came out in April. Here we see the time scale up to 2100, and here we see CO2 equivalent emissions. And the upper cloud represent the implemented policies, and with increasing uncertainty over time. And here you can see what we have promised, that the countries have promised under the Paris Agreement. And here you see what is needed to limit warming to 2 degrees or 1.5. This is what we call a gap. This is a very clear gap and a very strong message. So I really hope that people remember this graph and see the gap between reality and what we're trying to do under the Paris Agreement. I spend a few seconds on this one. And then, when we talk about overshoot, we need to be very clear what we compare the situation to. So that's why I'm going to show you 4 different cases. Staying below a warming level, that's what we're trying to do. Exceeding a warming level and continued warming, that's what we're trying to avoid. Exceeding and stabilizing at a higher level, not so good. And the 4th one, overshoot, exceeding a warming level and then trying to bend the curve and return the temperature to lower temperatures again. And this is what I'm going to focus on now. But when we talk about possible future developments, we need to be very clear what we compare the situation to. What are we discussing here? And sometimes this is just messed up without the clarity that is needed. So here I have a graph showing what I mean by overshoot and what IPCC means by overshoot. First, we have a situation where we are exceeding a warming level. Then we have a situation where the temperature is declining. And for that to happen, we need these emission profiles. We need steep reductions and then crossing the zero line again, and then net negative emissions on the global scale. As I said, we don't know how to do that, and we will hear more about that from Rosie. So net zero and net negative CO2 are key elements here. So to illustrate very simply, two important aspects of overshoot is the magnitude and the duration of that situation. And we need to identify the key variable. We are talking about temperature and which level of warming, 1.5 or 2 degrees. We need to consider net zero and net negative, and how can that be achieved? What is the role of the non-CO2 gases, methane, nitrous oxide, and what time scale are we considering? The Paris Agreement does not indicate any time scale for the temperature, but I think it's relevant to look beyond 2100, especially when we talk about overshoot, because it will take time to get the temperatures down again, and because there are many elements in the climate system that respond on a much longer time scale than this century. So here I considered global mean surface temperature and emissions behind that. So what about the impact? IPCC is often using this way of communicating risks and impacts. And we call them reasons for concern, things that we care about. And we indicate the risk by the color code from undetectable, moderate, high to very high. And the bullets indicate how certain we are about the findings. And I think you have seen this graph before, the different reasons for concern, extreme weather events, and so on. And it's important, and we discovered this during the writing of the IPCC report, that we lack literature on what is happening to the impact. We have studied the impact as the temperatures are increasing, but we don't know how the system responds when the temperatures are going down again. So this is a knowledge gap in the literature. And again, for all the things we care about, biodiversity loss, how will that respond when we go down again? If we have lost a species, we will not get it back, of course. So going down this is a different story. And here we need more science. So I made a very simple illustration of the temperature change and time. This is the version of the figure you just saw a few minutes ago. And then if we look at impacts, here are 3 different ways that the impact can respond to declining temperatures. Some may not go away. There may be some irreversible changes, the blue curve, the upper. And some, the green one, may respond slower to temperature decline. And some impacts may follow the change in temperature. So this is something that we need to pay attention to when we consider bending the curve. So the magnitude and duration of overshoot have consequences for climate and for natural and human systems. It will mean additional impacts and risks, and we don't know the climate responses in the carbon cycle, the regional climate and extremes, the glaciers, the sea level rise. We need more research on this. And as I said, on reversibility and irreversibility, and what are the implications for adaptation. And what is needed from a mitigation side? Yeah, we need globally net negative emissions, and we will hear more from Rosie about carbon dioxide removal. And we also need reductions in other gases like methane and other short-lived climate forcers. And a sustained decline in temperature can only be achieved with globally net negative CO2 emissions, which we don't know how to achieve. And globally, net zero greenhouse gas emissions using global warming potential, the standard metric for that, implies a net negative CO2 emissions and declining temperature. So we have built into the system, the way we aggregate gases, a mechanism that may cause declining temperatures if we manage to reduce CO2. So there are some questions in the end. How do we know that we have an overshoot situation? Diagnostics may lag behind, as I said, where we actually are. And that is a challenge to science and how we communicate that to the policy process. It may take years to say that we have exceeded a certain global warming level. We have to be patient and watch the fluctuations and average that over a period. And declining global temperatures assume net negative CO2 emissions are achieved and sustained. It's not sufficient to have that in 1 year, but we have to keep them net negative. And it's an open question when and how we will reach net negative emissions. So my final slide is another version of the slide that Ben showed. 4 different scenarios. This is from the 1.5 report that are all consistent with staying below 1.5, but with very different contributions from fossil fuels, the forests, and BECCS, that is taking carbon out of the atmosphere, burning bioenergy, burning trees, and capturing the CO2 and storing it. That is negative emissions. And you can see the amount of fossil fuel varies across the P1 to P4 scenarios, and indeed also the yellow parts here, which illustrates taking CO2 out of the atmosphere. The problem is that this is easy to do in a model, but we don't know how to do this on the global scale. And there are many challenges here, not only to make it happen, but also side effects for biodiversity, water security, food security, etc., etc. And by that, I hand over to Rosie to look closer at this yellow part and the challenges there.
Yeah, so I was challenged with sort of summarizing the field of carbon dioxide removal, which is kind of a intimidating task. So it kind of feels a little bit like talking about the internet in 1998, talking about carbon dioxide removal in 2023, because as Ben said, the world is kind of finally paying attention to what we should actually do about climate change, and there's a huge amount of activity in this space, figuring out whether we can just emit CO2 and clean it up later. And when I say we, I don't actually mean us, I mean our children. And so reducing emissions enough to avoid 1.5 degrees of warming requires a much faster revolution in the energy and emissions than we are realistically seeing right now. So climate scenarios, as everyone said, typically invoke these negative emissions via carbon dioxide removal. And so what is carbon dioxide removal? So at the moment, carbon dioxide removal is kind of really more like an aspiration than an actual thing. And what I'm going to talk about is all of these ideas, which are kind of pictured in this diagram. And they're sort of all ideas that people think we can scale up to doing this sort of planetary scale engineering of the system to take CO2 out of the atmosphere and put it somewhere. And CDR techniques vary primarily in terms of where the carbon ends up in the end. So some of them it ends up in rocks, and some of them it ends up on the land surface, and others it ends up in the sea. And so I'm going to give an overview of these technologies in this presentation. I'm going to talk about how they work, why some people are enthusiastic about particular kinds of the technology, and sort of barriers to scaling up to the global scale. And so the first thing I'm going to talk about is DAC, direct air capture. So this is kind of probably the most straightforward type of carbon dioxide removal. It's just a big machine. It uses a chemical process and lots of energy to suck CO2 straight out of the atmosphere, sort of just hoovering it up. And take the carbon products and store them in underground reservoirs, typically sort of oil wells. It uses very little land. This is one near Zurich, and it permanently removes the carbon from the system. But it requires lots of power, so it requires 1,000 kilowatt hours per ton. 1,000 kilowatt hours is about energy use of a typical Norwegian house for a month, which is fine at the current capacity for DAC globally, which is about 10,000 tons of CO2 per year in kind of experimental facilities like this. Obviously, people have big plans to scale this up. So the US Inflation Reduction Act is investing $3.5 billion in creating 1 million tons CO2 per year DAC plants. So that sounds awesome and expensive. But if you think about, it's hard to think about big numbers, obviously. And if you think about what that means in terms of global emissions, I'm going to use this time travel analogy for CDR, which this David Ho from the University of Hawaii published last month. It's a really nice way of thinking about this. And his idea is that to communicate what this means, you say, well, our largest, most ambitious direct air capture hubs will take 1 million tons of CO2 out. Yes, last year's emissions were 40,500 million tons of CO2. So each hub takes us back 13 minutes in time when it runs for a whole year, right? So with the present emissions rate, the energy and cost implications of this are obviously too challenging for us to kind of rely on this kind of technology. If we scale our emissions down by, say, 90%, this might become a useful contribution to the net zero goal. And so, of course, then people think, well, aren't there easier ways to get CO2 out of the air? Don't plants do that? That's what they do for their job. And so this is what Jan was talking about, and maybe you've already remember this already. So bioenergy with carbon capture and sequestration uses the same idea. We concentrate the CO2 and put it into rocks. But instead of taking it out of the air, instead we grow fast-growing bioenergy crops, and then we take those to a power plant on trucks. We burn them in the power plant, and we take the CO2 out of the chimney. In doing so, we get energy, which is good. And so people have thought about this idea of BECCS as a way of sort of more easily scaling up CDR. And so in these IPCC scenarios that get us to 1.5, the ones with a sort of more realistic timescale for reduction of I shouldn't say realistic, less ambitious timescale for reduction of emissions, imply this huge kind of magical burp of BECCS, which happens in the yellow area. And so it's useful to think, where did these predictions come from? Who thinks we can do BECCS that much and why? And the answer is integrated assessment models. So an integrated assessment model are the tools people use to generate these scenarios about how the world's energy, economic, land use, food, and climate systems kind of get to these targets. And they're these fantastically complex mathematical sort of structures. And they like BECCS quite a lot. So what we do when we make these models is we tell the model, okay, you can choose between these different technologies. And this one, BECCS, gives you money from the energy that you've sold, and it takes CO2 of the atmosphere. And so when you say you can do that, or you can do direct air capture, it says, well, I'll do this one. This one just sounds really good. But in the real world, whether BECCS is useful or not depends on what was there before. And so when you go to an ecosystem and you're like, I'm a farmer, and start growing some bioenergy crops, if you had forest there before, you cut down that forest, you create an emission, obviously, and then through time, you draw down some CO2 and put it in some rocks. But it takes you a long time to get to the point where you're actually net negative with your BECCS. And so for forest ecosystems, that can be 50 years or more. For pre-existing cropland, it can be sort of a fraction of that. And obviously, marginal land is best, but marginal land is where we weren't growing things before, probably for some sort of good reason. And so some colleagues of mine from the UK did this study where they tried to figure out how the physical system would respond to the amount of BECCS that the integrated assessment models, which I'll remind you are mostly models of the sort of economic and energy system, how would the physical system respond to how much BECCS they foresee? And so these two maps are two different scenarios. One on the left is getting us to 1.9 degrees of warming, according to the integrated assessment model. And the one on the right is 2.6. And so the one on the left has a more aggressive expansion of BECCS. And this kind of like tasteful color scheme is showing that we need to use kind of like about half of our places where we have really good cropland for BECCS, which is terrifying. And so, and from all sorts of the perspectives that I'll get to later. And so they fed these maps into their climate model. And what they found was that actually you'd expect that the more aggressive scenario would take up more CO2 because that's what it's supposed to do. It's doing BECCS, it's storing carbon in rocks. But actually what happened is the stored carbon in rocks is the purple here, and the carbon that you emit from the land use change is in red. And they found that actually the more aggressive scenario emitted more CO2 than the less aggressive scenario. And so in the physical world, did the reverse of what the integrated assessment model thought should be doing in the sort of physical climate system. And of course, whether this is feasible is one question, and another question about BECCS is that people have argued that it takes us from addressing one of our planetary boundaries of the climate and kind of moving the problem towards a bunch of other boundaries in which human civilization has to maintain itself to become to remain sort of viable. And so BECCS has, of course, enormous consequences for biodiversity, for fresh water use, for fertilizer, for the impacts of the shipment and the harvesting, for the existing food system security, and for the sort of intensification and crop yield assumptions that we're making around how we generate those BECCS crops. And so people are very concerned about BECCS. In surveys, BECCS is the least popular type of CDR, increasingly so as time goes on and people understand what it kind of really means for the land surface. So people think this instead often. They think maybe we should use more nature-based solutions. And so nature-based solutions are the kind of CDR where the carbon ends up not in rocks, not in using as technological solutions, but in fact it ends up sort of on the land surface itself, in the soil, or the trees, or the plants. And so, so at the moment, in the absence of sort of scalable BECCS technology right now, lots of our national plans for the contributions that countries will make to the Paris Agreement through their INDCs use a lot of offsetting which comes from sort of forest land and afforestation or reforestation projects. And this is about 20% of the total pledges that are right now existing. And of course, it's worth mentioning that conservation and restoration of forests, particularly in the tropics, is a really important win-win for the climate and for ecosystems. And so to that end, this has been recognized for a long time, and the REDD+ scheme, which reduces emissions from deforestation, degradation in developing countries, was developed several decades ago to kind of facilitate the maintenance of carbon in forestry, in forests, in the global south, primarily in the tropics. And what a lot has been kind of studied and written on how you do this. And so basically the socio-political complexities of persuading people to keep ecosystems intact are difficult. And so REDD+ uses this concept of these three things that a carbon project has to do to be successful. It has to have additionality, which means it has to do a thing that wasn't going to happen anyway. It has to not have any leakage, which classically means, you know, if I don't cut down, if I stop deforestation here, it has to not just happen over there instead. And they have to be permanent, so they have to be have to be sort of safe from being deforested in the long run. And so because this is really hard to do, the UNFCCC rules on carbon stocks are quite simple. If you just increase the stock of carbon, you get a carbon credit. It doesn't matter when or where you do that. And there's a lot of emphasis on the monitoring, reporting, and validation of land carbon stocks, with sort of more satellite missions and sort of lots and lots of work in that kind of sphere is going on right now to see did we put more carbon on the land. That's really important to know. But the thing is that the terrestrial carbon cycle, forests, are how much carbon can be stored by forests is really tightly controlled by the CO2 in the atmosphere and by the climate. So this is like a circular problem. And then these simple rules that the sort of REDD+ and the United Nations Framework Convention have adopted don't really take into account the fact that this is actually a lot more complicated than we think. So forest doesn't do the same thing under all these different futures. And so what we work on in our group at Cicero is thinking about how the carbon cycle functions. And so what the tools that we use, as opposed to the integrated assessment models, which are more sort of economics and energy focused, is we use tools called land surface models, which kind of scale up the physics of ecosystems, from the sort of energy coming in and the physics of how that works, through the hydrology of how plants extract water from the soil and evaporate it into the air, and so on and so forth. And then how the carbon cycle, how things like photosynthesis and soil respiration are affected by all that. And so this field is trying to kind of make a really sort of physically based way of predicting how much carbon stays on the land going into the future. And so from this kind of type of activity, 3 sort of quite less well-known issues with land-based CDR have emerged in quite recently, in fact. And the first is that high emission warming, under high emission scenarios, carbon stocks are unstable. And so as the climate warms, we get more forest fires, we get more droughts, we get more heat waves, we get more insects. And in our land surface models, what we try and do is capture all of those threats to the carbon cycle in a sort of global modeling system. And obviously that is kind of ambitious and difficult. And so our models tend to give different answers. And that's because we are uncertain about how the carbon cycle will look in the future. And that's a fact. And so what's happening in this arguably slightly busy figure, but each of these 5 panels is a different climate model, okay, with a different representation of the carbon cycle inside it. All those things I just showed you. And where it's green, these are sort of latitudinal bands going forwards into the future. These go out to 2300, not 2100 like we normally think about. And where it's green, the ecosystem taking up CO2 in response to CO2 fertilization in the atmosphere. And where it's pink, it's giving it out. And so as you can see, as time goes on, eventually we get pretty much every model is saying that substantial fractions of the world are the carbon on their land surface is no longer safe. It's being emitted back to the atmosphere. So if we have a high warming, this is a real threat. And then the next sort of less well-known issue with land-based CDR is that the reason that most ecosystems take up carbon dioxide at the moment is because we've been fertilizing them by increasing carbon dioxide over the last few decades. And if you sort of go into this low emissions future, where let's remind ourselves, we're trying to offset our sort of residual emissions from things that are difficult to decarbonize, like aeroplanes and so on. We foresee some kind of residual emissions continuing into the future. If you're trying to offset those in a low emissions world, your forest sink goes away. So this is another example from our Earth system model. We have this, in the black here, we have this pulse of emissions that goes up and down, sort of reflecting a kind of one of these net zero scenarios. And then the green, as you can just see there, that's the land carbon sink, which a few years after we get to net zero, itself goes negative. Yeah, so land sinks can't be used to offset residual emissions in a net zero world by themselves. And the third less well-known issue with land-based CDR is that land use change affects the climate directly. And so this is a study from some colleagues in the Netherlands a few years ago. And what they tried to say was, since 1750, there's been a huge expansion in Europe of forestry practices. And so that has been mostly conifers and fewer broadleaves as time has gone on, and that's kind of probably mirroring what most kind of carbon capture projects are going to look like in the real world. And what they find in this study is that because the needle-leaf trees make the surface darker, that basically absorbs more radiation, and it absorbs more radiation so much that it offsets over the next century all the carbon that those additional forests took up. And so they note in their abstract here that the political imperative to mitigate climate change through afforestation and forest management risks failure, and this is recognized that not all forestry contributes to climate change mitigation. I'm going to skip this slide because I think I had less time than I thought I did. and just go to the end. And so the take-home message, and I think this is kind of echoing the community at large, is that none of our ideas around CDR are certain to work effectively at scale without major consequences. Nevertheless, we will likely need some CDR once emissions are reduced to offset those residual hard to decarbonize sectors. But because we are not sure of the effectiveness of any of these, we shouldn't be using CDR instead of reducing emissions right now. We shouldn't be saying, I'm going to keep doing what I did, and I'm going to buy some credits over there. That's not a viable strategy. One other kind of one of the important point is that trying to think about the interconnected science we need to manage this is really hard. Trying to simulate, take into account the economics and the politics and the climate and the ecosystems and biodiversity. This is in its infancy, right? We've only just begun to think about how to do this. So with that, I'm going to hand back to Ben, who's going to answer the question here brought up at the beginning.
So 5 reasons for optimism. The world has started taking climate seriously, remarkably so, in the last 10 years. The difference between the debate we're having now and the debate we were having 10 years ago is enormous. And so, irrespective, for a second, of the mechanisms that we're choosing to meet our net zero targets, the 80% of the world's economy has committed to a net zero target in some form. This plot shows when they've committed to a net zero target. So the yellow is the earliest, the black is the latest. But a large fraction of the world is now committed in some way to limiting climate change. When I started in this field, we were tracking the worst case pathway. We had a selection of scenarios about the future, and we were consistently always going along the worst one. That's no longer true. So in the spectrum of scenarios that we had, the gray ones are the worst, the blue ones are the best. We're now kind of somewhere in the middle of the pack. And so why is that happening? Well, one reason is that the models, the integrated assessment models, which Rosie was talking about, have consistently underestimated how fast renewables are developing and how fast they're going to grow. So this plot shows each year International Energy Agency projections on what they think renewables are going to do for the years afterwards, and the red line is reality. So renewables, solar in particular, has grown unimaginably fast. The fourth point for optimism is a plot I've already shown you, which is that on a global scale, we don't think there's any runaway feedbacks. We think that the system broadly follows these rules. If we stop emitting in 10 years, we stop warming, problem solved. So that's a reason for optimism. And finally, economically, it's cheaper to do something to do nothing for quite a lot of the mitigations that options that we have on the table. Fossil fuels are expensive. So these are different sources of renewable energy, but the full plot in the IPCC lists other sectors as well. Anything that is in blue is cheaper than doing nothing. That comes it's more than free. So we should just do it. So we're not doomed. So can we relax then? So I want to finish just by we've already talked about the fact that the big numbers are difficult to grasp with. So let's stop dealing with big numbers. This is our budget, 400 gigatons of carbon for 1.5 degrees. Let's divide that by the global population. We have 50 tons of CO2 each. Okay, that's our 1.5 degree budget. And so the average human on the planet emits 5 tons of CO2 per year. So that gives us 10 years. 1, 2, 3, 4, 5, 10 years. In Norway, we can double that. The average Norwegian emits 10 tons of CO2. So ethically, if we take a really simplistic ethical approach to this and divide the remaining emissions budget by the global population, but we're going to blow through our ethical budget in 5 years. 1, 2, 3, 4, 5. How does that break up? So we use 1 of those tons on road traffic, 1 of those tons on other transport, 1 ton on agriculture, 2 tons from oil and gas production. That's not the actual burning of the oil and gas, that's just the production of it. 2 tons from industry, 1 ton from energy supply, 1 tons from buildings, 1 tons from other stuff. And that total of 10 tons for Norway has remained pretty constant over the last 20 or 30 years. It's shifted a little bit between, so this is industry, which has come down over the last 30 years, but the oil and gas industry, and this is just their direct emissions, not the burning of the oil and gas themselves, has kind of grown to fill the gap. So maybe there's a little bit of a reduction over the last 5 years, but broadly, it's remained constant. And as Rosie was saying, a lot of countries have offset some of their emissions with assumptions about what the natural land is doing, and Norway does that too. So we have 10 tons, but then you subtract off 3 for the managed land sink. But this 3 is going to go away if we hit net zero, and it also might go away if the system warms and the forests burn down or get eaten by beetles or something that we're not yet representing in our very simplistic models. So we talked a little bit about the natural gas industry, the oil and gas industry before, but let's change the way we're doing the calculation now and look at what the emissions are from the production of Norwegian oil and gas, which is 45 tons per person per year. That's the actual emissions from the oil and gas which is produced by Equinor. And so that blows through the entire ethical budget in 1 year. So can we relax? No, but that's all I have to say.
Yes, thank you. My name is Mats Rinaldo, DNV. Thank you for interesting presentations, all of you. This goes probably to Jan. I was wondering if there's any consensus in the science around what temperature long-term that we should stabilize. So we're trying to avoid anything above 1.5, but in your P1 to P4, I see net negative emissions in 2100. And I was wondering if there's any discussions on if that should stabilize to net zero long-term, 2100, 2200, or it's kind of weird that there's a cutoff at 2100 at -5 gigatons. And are there any discussions on whether we should continue down to 1 degree, 0.8 degree, or same pre-industrial levels? Thank you.
I'll collect a few more questions before you answer. It was Jan Ivar and then the man in green sweater.
Yeah, so I really have one comment and one question. So the first one is just a comment to Rosie. Like you made a remark there that I think it was that that nature-based climate solutions can not be used to offset residual emissions, which you kind of passed by very quickly. But I think that's, in many circles, that is a bombshell that needs to be shouted from the rooftops, which I'm sure you're aware. But just that message needs to be shouted out there. And then just one question for Ben. So you said that. I think you said that we don't think there are any tipping points, but I assume there are some qualifications to that statement. So if you could just just say what the assumptions are there.
I'll take one more question, gentleman in green sweater, and then, yeah.
Thank you. Thank you for some very interesting presentations. My name is Christian Rødland. I'm a senior medical officer at the Norwegian Institute for Public Health. I was also wondering about the tipping points issue that you mentioned, Ben, because I know that Rockström and colleagues published a very interesting article on that in Science half a year ago. And I, of course, that is, we tried to say something about the future, which is, of course, uncertain and based on certain models. So maybe that's only adding uncertainties to what's already uncertain. So if you could comment on that and say something about how tipping points is included in the models that you present. I just want to give a very brief comment as well. I don't fancy the word being doomed as you used at the end, but I think we should be very careful. It's ethically questionable to sit in Norway and sort of not take into account the seriousness of the situation, thinking about the global south. Thank you.
Great, thanks. Jan, do you want to go first?
Yeah, can you hear me? Yeah. So regarding the time scale, it's a very good question. And as I indicated, I think we need to go beyond 2100. But 2100 has been the usual time scale, and this is not a conscious choice. I think this is given by the modelers. So of course it's difficult to model the economy, the global economy, beyond 2100. But in terms of what is needed for the physical system, I think we need to go beyond that. And there is no clear decision, but there is a lot of discussion about this issue. So I think that's all I can say at this point. But I think we will expand the timescale in the future. We have to.
Yeah, Ben, you want to go next?
Yeah. Yeah, on the post-2100 issue, it's yeah, I think it's critical. And are there impacts at 1.5 degrees? Do temperatures have to be lower than 1.5 degrees long term? I think that's a relevant question, which is connected to the tipping point question, which I'll come to in a sec. One of the problems is a lot of the models are hard coded the economic models are hard coded to 2100. So getting that community to switch is going to be a battle. But I think it's important. On tipping points, so first point, I think that there needs to be a different discussion about process and regional tipping points, of which there are many. The Antarctic ice sheets, coral reefs, rainforests, individual ecosystems. There are lots of different individual tipping points which very likely exist and will very likely be triggered at some warming level, and we should be very worried about that. The point that I was making was regarding global temperatures, whereby the first order approximation that a unit of carbon gives us a unit of warming has remained pretty robust in a wide selection of models now. The correction to that, there's a whole community looking at the errors in that approximation, and that's called the zero emissions commitment. How much the system warms if you're not, when you hit net zero, and you shouldn't be warming by this relationship. And I guess we're still learning more about what that looks like in different models. But with the models we have at the moment, it's a small correction factor. It's not the dominant thing. You don't expect the system to significantly warm by another degree or so once you've stopped emitting. The caveat to that should be that's with the class of complexity of models which we currently have. So if there's something huge that's missing there, if there's a vast oversimplification in the carbon cycle as we're currently representing it in climate models, then that's a caveat on that. But with the best knowledge that we have at the moment is that the system broadly, globally behaves according to this cumulative emissions framework. Yeah.
Rosie, did you want to pick up on Jan Ivar's comment, or?
Yeah, and so I agree that it's alarming and needs shouting from the rooftops. I guess a point is that in the sort of IPCC process it stands, the IPCC being the biggest rooftop, this question falls through the cracks of the process because we have all these different representations of how the carbon cycle works. We have some in these integrated assessment models which work out the scenarios and land use that we feed into our Earth system models, and they run those scenarios, none of which were particularly aggressive in the last round of simulations. We didn't actually get to the point where we were doing those simulations, and even if we're not actually running, most climate model simulations are driven with atmospheric CO2. Right? They're sort of they're sort of driven they're driven from the perspective of someone with a dial on the atmospheric CO2. They're not actually driven from the perspective of we're humans, and what are we going to do to our emissions and the land surface? Those are the levers that we have to actually kind of operate the climate system, if you will. But when we do climate simulations, we don't actually address the problem in that way, and so there's a big push to kind of make that, to change that, and to kind of have a more ambitious view on how we understand the Earth system, so we can make more robust statements about what happens under net zero to our forests. Your question about what's the ideal temperature in a world where we magically acquired a dial, right? Kind of what this is all sort of implying is like humans are kind of aspiring to have ways of controlling our CO2 emissions, and with the geoengineering angle, even more so. And the minute you get into that world where you have a question about what's the ideal climate, the question, it becomes like, for whom? And if you live in Canada, your question answer to that might be slightly different to if you live in Bangladesh, and so it immediately raises all these kind of issues of power dynamics and inequality, and who is being harmed by the tactics that you're using to control the climate, and who is gaining. And so I think that's from a solely human perspective, that's a very difficult question to kind of even think about addressing. From a sort of ecosystem perspective, I think it's simpler because our ecosystems are all adapted to the climate of the last millennia, right? And so they're sort of cycles of pollinators and phenology of plants and migration patterns of birds and so on. Those are all very, very tightly knit to the current, or the pre-industrial climate. And so I think from a sort of nature perspective, it's important to be kind of consider the complexities of the biosphere when we're trying to answer that question.
I have a question while I'm waiting for more hands. Okay, there is a lot of hands. Then Kjetil there, man in blue shirt, and then at the back. And here also. Let's capture those 4 questions.
Yeah, okay, Kjetil Aas, Cicero. I was just going to follow up with a question on what's the ideal temperature. And Jan, you had this figure of impacts, but could there be negative or impacts as you go down in temperature? Maybe Rosie could answer from an ecological perspective. But at what point do you actually want to keep the temperature that you have reached? And are there kind of further damage as you go down, and if you go down steeply?
We will collect a few this time also. I think it was the man in blue shirt there, and then the gentleman at the back, and there was a 4th hand there. Yeah, okay.
Thank you. Yeah, my name's Henry from DNB. Just wondering, it's actually a follow-up to Jan Ivar's point, not to rehash it, but there are, I think, many large corporates out there that are using offsets in their sort of commitments to net zero 2050, and then many of them are sort of arguing that when they see these climate models that are out there, that there are sort of a large portion of it which assume sort of these natural carbon sinks. I was wondering, have there been any efforts or attempts within the different modelling agencies to remove those from the climate models, just to sort of, or at least begin them sort of in a post-net zero world, so that way, they can't use it? Because I guess that's the main justification we hear from when we talk to companies, is that they say, oh, well, we see it in the models that, you can use these nature-based solutions. So, because I think it's to Jan Ivar's point, it's a really big and key issue that we need to sort of have shouted from the rooftops that this isn't possible.
Yeah. Great, thank you. And then at the very back.
Hi, Marian Graf from MF. I'm wondering, you mentioned earlier that IPCC consistently underestimated the growth of renewables. If one of you could, or several of you could comment on how that growth of renewables, which is in some ways a huge relief and maybe is saving our asses, how that also can be done in a sustainable way so that we don't have this continuation of green colonialism where indigenous peoples and nature that is being preserved are being destroyed in the process of trying to get at these resources, and also the kinds of companies and industries that are now smelling, new profits. Is there a process? Is the IPCC or CICERO involved in any kind of way in looking at these kinds of issues? Thank you.
And then the final question here by the aisle. And then we need to close for the questions and have a quick round of answers from the panel.
So I'm Knut Einar Rosendal from Norwegian University of Life Science. I'm questioning about direct air capture. As you mentioned, it's very small today. So I'm wondering about what are the potential for scaling it up, both when it comes to cost reductions, more energy efficient, and also storage of the CO2.
Great, thank you.
Yeah, I can start responding to the question about what is a safe level of temperature change. And there, of course, there is no clear scientific answer to that. And for many years, 2 degrees warming was seen as the safe limit. But then in the preparations for the Paris Agreement, many countries said we need to stay below 2 degrees and aim for 1.5. Again, 1.5 is definitely not unproblematic, and many parts of the world already feel that we have crossed a level where we're not safe anymore. And then going down, as Kjetil asked about, actually we don't know exactly how the impacts and systems react to going down. And we need to keep in mind that change in itself and rate of change is a challenge for the system to adapt. So for some impacts, I don't know, but it may perhaps be better to stable and give the system time to adapt than perturbing the system again and going down. And as I said, we need more science on these topics. I think Rosie can follow up on that.
Yeah, it's a very hard question to answer. I mean, one thing is, our understanding of how ecosystems are being affected by rising temperature is pitiful. And kind of naively, you might imagine, well, if we push a system into a hotter, drier climate and we lose a bunch of species that were adapted to the previous climate, then we come back and we have an even more impoverished system when we go back into a scheme where we're losing the ones that are more adapted to the warm. And so yeah, my sort of straightforward assumption is that, let me just stop working, is that would be, in some way slightly more damaging, but our understanding of this is very poor. And then the question about the scaling of DAC. I'm not really an expert on the scaling of DAC, I should say, but there's a really good report from the IEA on the sort of. I didn't get the light that I read in preparation for this talk, and I didn't get the impression that they were necessarily sort of seeing a bunch of innovations coming down the pipe in terms of DAC. But of course, we never know, right? There's a lot of innovation happening in this field, so I am not the one to make a prediction on that front. And then talking about the sort of urgency to get this message made more public. I agree. People are writing on papers. The fact that carbon sink goes away in intact forests if you stop rising CO2 is not particularly controversial in my field. But when we provide, when information is provided to IAMs from the sort of more forestry based studies, they only take really one number, right? They say if you convert cropland to forest, then its carbon density goes up by this, right? That number is not dependent on the pathway, right? Because integrated assessment models have to iterate, right, across lots of different futures, and so the number of the carbon that they use is just one number, right? And so it doesn't know whether it's in a high CO2 world or in a low CO2 world, right? Just for like mathematically mathematical reasons. And so
we are starting to run out of time.
Yeah?
I just
Sorry,
want
yeah,
to
yeah.
make sure we also cover the question that was on renewable growth and in a sustainable
Yeah.
manner. Anyone who wants to take on that?
But I agree it's important, and I'll take any megaphone going to make this point.
Then maybe you want to take the renewable growth question.
Yeah, can I say one thing on the other thing first, which is that on the benefit of temperature coming down, like one of the biggest problems we have at the moment is there's multiple things changing at once. Carbon dioxide concentrations are changing, temperature is changing, and so all we can observe at the moment is what the response of the system is to continued nearly flat emissions. And so as soon as that changes, as soon as emissions go down or they go negative, everything kind of goes out of the window, and we're in a much deeper sense. It's kind of easy to kind of say what the system would do if we just kind of carry on emitting at the same rate. But like there are more uncertainties in what the system will do as emissions go down, and even more uncertainties again about what they'll do when we go negative. And so in that negative period, a friend of ours, Charlie Coven, once said that this is like potentially the worst time to be a tree, because trees like carbon dioxide, and so carbon dioxide will be coming down at this point, but temperatures would still be high. They may be still going up, you know, if there's some residual warming or ZEC. And so that's a deep state of uncertainty for what the ecosystems would be doing in that negative emissions phase. We really don't know. That's point one.
Well, the second one has to be really quick, because we need to wrap up now.
Okay. Yeah. Renewable growth, sustainable trade-offs. Yes, you're right. Of course, the cost expansion of renewables has to be done in a cost-benefit framework when you're looking at the potential damages to renewable expansion to other aspects of the ecosystem. But that has to be compared against what the alternative is. So if you do the cost-benefit framework, you also need to look at what the costs are of continued what you would do in the counterfactual scenario where you didn't have that renewable expansion. Would you have a reduced energy demand? What would be the consequences of that reduced energy demand? Would you have continued oil and gas production? What would be the consequences of the continued oil and gas production? So I agree that there shouldn't be you know, there shouldn't be a carte blanche to do anything with renewables, but we have to look at this from a system perspective, not just in isolation at an individual ecosystem, with or without renewables. It has to be global, national assessment of what the cost of different futures are.
Great, thank you so much. Then I would like again to thank the presenters, and thanks to all of you who have been participating and also online.